Okay, so we're going to continue on with relativity today, and what we're looking at today is general relativity. This was still developed by Einstein. And remember, our issue was we had Galilean relativity, and we had an issue when we started approaching the speed of light. So Einstein came along and he said, okay, let's look at special relativity, and he said everything works in physics from inertial reference frames. The only caveat is that the speed of light is the same in all reference frames, which is a little bit odd. So, if we can remove that issue of inertial reference frames, then physics works all the time. Well, that's what general relativity does. It removes the restriction of inertial reference frames. Now remember, inertial reference frame says that non-accelerating reference frames. And we do this by saying gravity is the same as acceleration, which is a strange idea to contemplate. But we just got to remember that uh, if we think about gravity um, as being the main focus of general relativity, it'll help everything out. Uh, Gravity is the same as acceleration. If we don't have a frame of reference, um, like if we're in space and we can't see anything else, we don't realize that we're actually falling towards the greatest gravitational pull closest to us. Um, because we have no frame of reference. That's the idea, is that acceleration is just the same. It's just there. We get this from he thought of space and everything as matter existing. Not that matter was attracting itself, matter to matter, like we do with the universal gravitational formula, but that gravity or mass bends the space-time um, material, and it it bends it, and so then bigger masses create a bigger bend, and therefore you roll towards that bigger bend in space time. The video after this that I've linked in the lesson plans demonstrates that. It's a very interesting concept. I think you'll enjoy that video. Look at it as bending space time. It's an interesting take of it. So, if we think of gravity as being this all powerful aspect of it, which is interesting since gravity itself, the way we've calculated, has been a lower um, force. That universal gravitational constant is like times 10 to the negative 11th. Um, but it has such a bigger impact because we can put so much more mass to it. If we have a big enough gravitational force, we get, when we start dealing with gravity and light, we get what's called gravitational lensing. This is when the gravitational force is so strong that gravity attracts light. In other words, it causes light um, to bend. So if we have a large gravitational force, light will bend around that gravitational force. In fact, if it is so strong, if we get a gravitational force that is so strong, we get what is called a black hole. And this is where light and everything gets bent into the black hole. Everything is attracted into that, including light. Everything goes into a black hole. And it's just a phenomenon. We've seen evidence of the corona. Maybe I should link that too. I'll try and link that too in our lesson plans, is the evidence of the black hole captured on video that just happened last year. uh, last year, as in 2019. Uh, Now, general relativity, the scientist you need to know for that is Einstein. Black hole, the leading authority on that, um, has been Stephen Hawking. Now, that was true when he was alive. I'm not sure if anybody has taken over his. I don't know if there's been any enough discovery since his death recently. Um, if someone else has come to be the more forefront scientist on that, but he has been the leading scientist, physicist um, on black holes for a long time now. And so let's just keep all that in mind. We had general relativity, or I'm sorry, we had Galilean relativity. Uh, Issue was the speed of light. Einstein came along and we had special relativity that took care of that. The issue then was the inertial reference frames. Einstein further developed relativity into general relativity and let gravity take care of that issue. And that's where we are today. And both of those ideas are still, all of those ideas are still highly applicable. But if we're talking about relativistic speed, so the speed of light, we're going to talk about special relativity. We're going to be talking about gravity. We're going to be talking about general relativity. And in slower speeds and normal situations, we're still talking about Galilean relativity.